So I'm Shu Yang from Material Science Engineering and at Penn. So I'm the co-leader of the ACT1 with Robert Riggleman. And so what we're trying to do is address is the question of the coatings for the water harvesting, water collection. And so let me just present you this problem first. So as you see here, there's a lot of issue in terms of the how do you get the water in the arid region. So the first example I'm trying to show here is in Namib Desert, right? So the precipitation is only about 2 to 200 millimeter per year. So think about this. When we're talking about, typically we're talking about science, we're talking about nanometer, micrometer, but this is in millimeter is actually a very, very small percentage in terms of the water precipitation. And on the other hand, you go to look at the other example is Lima at Brazil. Lima has very high humidity. However, how do you collect the water, right? So they have high humidity, but they don't get the water because they don't have a lot of rainfall. It's similar like in California, we have beautiful weather, but you don't get a rainfall. So the rainfall is a little bit higher. It's 1.5 centimeter per year, and not much better than the Namib Desert beetle, which means you don't get a lot of water, and even worse is 70% of the population lives on the arid Pacific coast region, all right? And this is only 25% is the water source, where the water source is coming from, and 70% people living on this area. And also, in this case, as you see the images, in Lima, it's not flat, it's actually very hilly, all right? So if you want to deliver the water, it's also very, very difficult. So actually, about over 1 million people are not connected to the city water. So how do they get the water? When they get the water like this. It's not coming from your tap water. So people really, they have to deliver the water from the trucks. And when the water coming to the trucks, then they take those tanks, and people open the tanks, collect the water, and use that water. So for each family, a regular family, it's $25 per month. You think this is very small amount percentage, it's $25. But then you think about this is in Lima, Brazil, and $25 is a lot of money, all right? And you don't get this from, you don't open tap, and you have to collect them, all right? So it's actually very expensive, as this pointed about this by this New York business editor mentioned about it. It's a high price for poor, all right? So if you look at the bigger picture, even worse is actually this is a global crisis. It's not just from Lima, from the desert. So over 5 billion people is actually living in a high water stress region, which is 40% of our population. All right, and so really it's a global problem. So which means we need to have a global solution to address this as early as possible. So here, as mentioned earlier, there's a 3-act. It's a collaboration between Penn and Giant, right? So as ACT1, our goal is eventually, so we want to have combined research and education. Eventually, we want to develop a technology addressing the coatings. And this coating can capture water via condensation or trapping of the droplets. And then we can, once we collect the water, you want to collect the water, right? So collect water, which means water has to flow, and you want to divert, recover, and purify the water via the infiltration and anti-fouling. But to reach this technological endpoints, you need to have a combinatorial approach, which means you need to address fundamental questions first. So we need to have a collaboration between Penn and CNRS, the Giant, is to understand what are the fundamental questions in this area in terms of the wetting, the energy flow of the water. And our goal is to introduce nanoparticles, nanowires, and different kinds of polymers and different kinds of hierarchical substrates. So then we go back to look at this, is how to solve this problem. So then actually look at the nature. We have to go back to nature and see how nature solved this problem. So we have to find the cues. So going back to look at the desert, the Namib Desert, right? We said they have very, very low precipitation, and they have been over millions of years, tens of millions of years. And one interesting aspect, though, is that during the day, it's 45 degrees Celsius, all right? At night or early in the morning, it's actually 0 degrees Celsius. So let's take a look at this picture. So this is a Namib Desert beetle. It's not dry, it's wet. How they do this? How they get the water? All right? So they actually get dew water. So what people have discovered is actually on their scale, they have a very interesting scale. So the scale normally is hydrophobic, it's covered by the wax. But certain region on this hemisphere bumps, they have this hydrophilic region has no wax. So that's where the water is actually will sit onto those surfaces when they grow bigger, and the gravity will drop them to roll along those hydrophobic region. Then they can actually roll to, and also you notice they're very, very smart. They always put the head down, is because the water by gravity will roll to the mouth, and they can drink the water, all right? And recently there's also another example is looking at the cactus. Again, the cactus has very interesting aspect is they have this kind of nanowire or the shape. So they have hierarchical wires, micro and nano. And water, again, is how they condense onto those wires and how they flow and how they collect water. So there's a lot of research in this area in terms of going from initially super hydrophobic surfaces inspired by the lotus leaf and going now to how do we actually condense the water, how we collect the water, how we nucleate the water, condensation and growth. So for our ACT, our question we want to address is, in terms of fundamental question, is how do we differentiate ourselves from all the other water collection, water harvesting technologies? Right? So we want to ask the question is, what is the optimum sites in terms of water collection and droplet growth? And what feature geometry? So remember, you saw two examples from the desert beetle and also the cactus. The geometry is very important, right? And hierarchical geometry is important. How do we design the geometry? What kind of geometry will be optimum in terms of steering the droplets and location for the water collection? And although many studies so far is trying to understand the equilibrium state, for us, there's a lot of question is, how do you actually take advantage of maybe harvesting the kinetic strategy and to go look at non-equilibrium behaviors, all right? How important it is. Can we create pinning sites for water collection and overcome those pinnings and control the water flow? And also, can we exploit the evaporation gradient, for example, and associated surface tension energy gradients to actually control the droplet motion? And last point, all right, for today's talk is how robust those coating is, because as a scientist, when we're looking into this as researchers, we're always coming up with many different ideas to manipulate different kinds of coatings. But to implement this as a technology, right, you need to use them. You have to understand the practical issues. And one of the practical issue is how robust it is. So this is actually much harder than the typical science is trying to make them useful. And of course, another question is how much you are going to pay for this. So the cost is very, very important. So that's one of the other interests I forgot to put onto this slide, the question we want to address. Right? Oh, yeah, it is. Okay, so the scalable manufacturing. So how do we actually scalable this and to go lower cost? And so first example I want to show you is coming from my lab is we're trying to understand how we control the water nucleation and growth. So there's a lot of understanding and people trying to mimic this. The Lambian desert beetle is you need to have hydrophilic patch, you need hydrophobic regions. And so we started to ask the question is that necessary? Because to make them, it's relatively difficult because imagine you make something, you need to specifically introduce the hydrophilic region. Can we actually start it with a chemically homogeneous surface and then play around with the surface geometry, the hierarchical behaviors? So for example, Yonghong Chang in my group, so he used this AO template, anodized aluminum oxide as a template. And then we couple with photolithography, then we introduce these hierarchical structures on the surface. So I have micropillars on top of it, we have nanopillars. All right, so our question is, can we use this to either encourage or discourage the water nucleation? Because this is actually also coming from the CNRs, because Daniel Bison, during this process, when we started to talk to CNRs, so he actually has a theory. He identified 4 regions of the water nucleation. One of the smallest region is, he said, if you have submicron features, this will prevent water nucleation. So we want to test out his theory. So we fabricate this. So this nano pillar is about a few hundred nanometer, and underneath we have micron size. So if the theory is correct, and then we should, on these nano pillar covered region, we should not see the nucleation. All right? And so this is exactly what we saw. So we purposely identified some good region and bad region for the comparison. So this is the environmental SEM. And we saw here, for example, you saw this is a pillar and this is non-pillar region. You see when you started to increase the pressure, we started to see water nucleation between the grooves, and then keep growing and growing, covered, and then you have a lot of water coming out. However, if you have a good pillar region, you never see the water. But if you have a bad pillar, so this is non-circle, the rest circle region, you started to see water started to coming out. Right? So this, in some way, we think it started to be consistent with Bison's theory. Of course, there's a lot of questions we need to address. That's what we are trying to do in this act. And the other example is, well, if you have the water nucleated, so they just, where do they go? Do they just random pop out? So our question is, can we actually guide them to go to the place we want to collect? So for example, we have this pillar, which is super hydrophobic, and this region, you can see here, water does not like to sit on those surfaces. If we shear the pillar, pillar will be light down, then you see all these become isotropic 1D structures, and all the liquid will actually collect on this region. Right? So there's a lot of things we can play around with the geometry and control the guiding of water shedding. And likewise, there's some example in the butterfly wings, and they use this mechanism to shed off the water. And then comes back to the question, if we collect water, how do we actually purify this, right? We don't want to, of course, if you do this water condensation, that's pretty clean. But if you just do the regular water shedding and collection, it may not be very clean. And so this is another great example to show the collaboration will be very useful. Is actually in the giant, there's a lot of interest to understand this different kinds of photocatalytic nanoparticles and nanowires. One aspect is you can use this to control the wetting. On the other hand, all of these things is actually also very useful for antifouling, antibacteria. And further, they can design a material to make them photopatentable. So you can pattern this kind of regions and pattern these surfaces. So which will be a great synergy between Penn and the giant by patterning these different kinds of nanowires, nanowire mesh, introducing different kinds of surfaces. We can put in different materials. Just give you one example. So this is actually, we pattern the surfaces with these high aspiration pillars, and then we can purposely decorate those surfaces with nanoparticles. Imagine we can also do this decoration with nanowires, nanowire mesh. And so we show here the nanoparticle act as a mushroom surface. So we can introduce superhydrophobicity, also superoleophobicity. All right, so the antifouling is not just anti the water, it's also very important anti-oil, the low surface energy contaminants. And further, if we change the spacing between these pillars, we can make them transparent. We can also pattern this, so you have this windy anisotropy. You can guide the water flowing. All right. And so coming back to here is, I talk a lot of this is patterning, but also there's a lot of interest in terms of the nanoparticle and self-assembly. So one is top-down approach, the other one is actually self-assembly. So if we can self-assemble particles on nanowires, then we have another way to scalable manufacture them. So one example, oftentimes people were talking about spherical nanoparticle assembly. So what I want to show you here is, well, there's another set of nanoparticle. If you chain a nanoparticle together, you actually get string of the nanoparticles. So they are not nanowires because they're much more flexible. It's like the polymer chain, all right? When we talk about the polymer chain, we always say it's a pearl as a pearl. So if you chain them together, so they're flexible. On the other hand, they can aggregate, they can self-assemble into this kind of more porous materials. So because of increased porosity compared to this kind of spherical nanoparticle assembly, we generate this kind of fractal surfaces which can prevent the oil wetting. So not just the super hydrophobic, it's super oleophobic. We call it super amphiphobic surface. So controlling the porosity, utilizing different kinds of morphology of the nanoparticle is critical. And then because they form this mesh, right? So they form a network. So which means you can transfer this by simply spray coating onto a paper towel. The paper towel we use all the time in our lab. And so this is a support, microscopically porous. And then we spring those nanoparticles on top of it. And then we can manipulate because it's amphiphobic, so we can make them water wettable or oil wettable, so we can use the same substrate to separate the oil or separate the water by engineering the wetting condition. And so then comes back to the question is, well, how do we make them scalable? And so we can do this oil-water separation, so eventually you're making the membrane, right? So think about the membrane. So when you flow something through the liquid, through the membrane, on one hand, you want to have this membrane very high the selectivity. You want to filter out the bad things. You want to have the clean water or oil going through. But on the other hand, if you're going through this way, you're trying to make the pore smaller and smaller, you also have the issue of the permeability. So it's always a question of, it's always very difficult to balance this, to have the permeability and the selectivity. So question, how do we do this, right? So, we come up this idea. So this is De-Jong Lee, and coming to this question is, how do we generate nanocomposites? So can we have a porous support and introduce a dense selective layers? And one of the ideas, of course, going back to use nanoparticles. So if we can have nanoparticles introduce this nanoporous membrane, can we enhance the mechanical stability? Because nanoparticle, if you just, even though they contact, it's very easy to take them off. So how do we enhance the mechanical strength? Can we use polymer? So if we use the polymer, how do we actually make them more interesting, right? So here shows one example, and showing the nanoparticle infiltration through the bottom polymer going into the nanoparticle, more or less fits into the locus washbone dynamics, right? So the question is, well, if we want to make a membrane should be porous and should not be completely infiltrated into those interstitial spaces. So the question is, how the particle is interacting with polymers, and how is the wetting, de-wetting encouraged, although they infiltrate, to polymer should glue and connect the nanoparticles. On the other hand, you still want to maintain a high porosity. So what is the preferable wettability between the polymer and nanoparticles? And what is the polymer size? And what is the chain size? And what is the dynamics of this kind of migration and so on, right? So that's why we need to have the simulators to help us to understand this before we do the experiment. Of course, we do the experiment, but it would be nicer to have somebody to give us some guidance. So fortunately, we have Rob Riggleman in our chemical engineering, and so he's doing exactly this kind of things with Russ Composto, with Zara, which is perfect for this ACT1, is to look at, so let me, hold on a second, let me play the movie. I don't know. So where's the movie? Yeah, somehow just, oh yeah, okay, all right. So as you can see here, so depending on the molecular weight, depending on the temperature, so for polymer to move is you have to heat up above the glass transition temperature, right? So the question is, what's the thickness of the polymer? What's the molecular weight of the polymer? We control the dynamics. Are they the same? Do they have the similar TG? They migrate similarly? So that's the question we want to address. So this is in the early simulation, they show actually they're not exactly the same. All right, so some of already reaching the mobility, but not everybody. So in the center or the edge of the film, they are not exactly the same. So then the question is, how do we control this? So how do we manipulate the glass transition? And this is showing another example, is to show here, look at the green curve. I think this may be also a movie. Let me see whether I can turn on the movie. Oh, yeah, sorry, I can't turn on the movie thing. So anyway, so this, what you see here is when you have this dynamic motion, right? So depending on the molecular polymer chain size, so polymer chain actually has this so-called stretch and hop. So when it moves, so this is, there's some kind of entanglement or motion of the polymer, but then they will stretch when they move, increasing the time scale, then they actually go back to collapse. So the question is how they move. Can we actually freeze them in any of those stages? Is any of the stages actually advantageous? During this, remember our goal is to make a membrane, but the membrane has to have a porosity. We need to have a cavity, right? At the same time, you want to have the polymer to connect with each other and grabbing the nanoparticles. So there's a lot of questions, very rich questions for us to address in this ACT1 in the next 4 or 5 years. So that's another example. Oh, let me see. Uh-oh. Yeah, so this is another example is coming from industrial question is, can we, again, make them manufacturable and making those membrane potable? So this is a collaboration between the Solvay CNRS through the Compass and with Penn. And so can we design this kind of nanoparticle, not just the nanoparticle assembly, can we have the nanoparticle assemble into this microscopic scale, into this colloidosomes? Right? So can we introduce the colloidosome and with a nanoparticle decorated onto those surfaces, and then we make a membrane? And so can we make this more efficient in terms of the manufacturing? All right. So again, this nanoparticle doesn't have to be, can be any kinds of nanoparticle. Could be silicon nanoparticles, could be particle is decorated by the polymers, could be gold nanoparticles, or could be even nanowires. Right? So there's a lot of rich question is how do we actually interact between ACT1 and ACT2, which you'll hear very soon. And the other question is, if we have those, all these films we've fabricated, we need to characterize them. As we know, Giant has this beautiful facility we can take advantage of to characterize. So this is one example, use the Grazer incidence X-ray to characterize the nanoparticle migration. So in this case, we have a liquid crystal. We have a nanoparticle assembly underneath, and we put the liquid crystal on top, and liquid crystal introduce topological defects. And then we heat it up, the nanoparticle migrate through those defects. So now, so I turn the table around. So everything we're talking previously is we're trying to migrate the polymer through the nanoparticle interstitial space. And can we do the opposite way, is actually we introduce polymers or some other mediums, and then introduce nanoparticle migration through those defect regions, through the porosity, through the cavity. All right, so this is a different approach. So I think there's a very rich question is for us to answer is how do we manipulate this? Can we actually pattern this? Can we purposely introduce defects, control the particle assembly? And so with that, I think I'll stop here. I'm sure you'll hear a lot of talks in other acts, all right? So I'll be happy to stay around if you have any other questions, all right?